Good afternoon, everybody. Welcome to the MREA Exploring Energy series. We'll give it a couple of minutes before we get started. Get everybody in from the waiting room. While we're getting rolling here, you can introduce yourself in the chat. Let everyone know who you are, where you're joining the call from, and if you have any affiliation. Glad you're here. Okay, we are 2 minutes past the hour, so we will go ahead and get going. Good afternoon, everyone. Welcome to the Exploring Energy series presented by Montana Renewable Energy Association. My name is McKenna Sellers, and I'm the Executive Director of MREA based out of Helena. And this is December, meaning it's our final Exploring Energy series of 2024. The Exploring Energy series is a monthly lunchtime presentation where we cover energy issues impacting Montana and beyond. We hold these once a month at noon to explore renewable energy technology, the latest trends in energy development, and connect with experts working in the future of our energy system. And last month we talked about geothermal. This month we're joined by Nathan Bronec of Cushing, Terrell to talk about solar readiness in new build design. So we're very excited to be here. We'll run through a couple of announcements and then get going with the presentation. For those who are new to MREA, we are a 501c3 nonprofit organization. Our mission is to foster the growth of renewable energy in Montana through education, advocacy, and industry engagement. Next year, we're turning 25 years old, so very proud to have that 25-year history behind us networking for the good of renewables in Montana and the people that we serve. For those who are members, and membership is open to renewable energy consumers, supporters, and industry professionals. So if that interests you, we've got a QR code coming your way here shortly. And we're also electing our next tranche of board of directors. So if you are a member, you should have received a virtual ballot, and elections are open until December 10th. So take a look at those candidates and our next generation of leadership for MREA's board. And because this is the year-end giving season for the nonprofits like us and many others across Montana, had to make an announcement that we have launched our Power 2025 year-end giving campaign. And so if you're supportive of the type of work that MREA does, if you like our Exploring Energy series, and if you want to continue to see MREA do good work for Montana at the legislature, at the PSC, and in communities all across the state, we encourage you to support MREA and keep us a sustaining and strong organization as we power up for the legislature and beyond in 2025 with a year-end gift to our Power 2025 campaign. And I already see in the chat there's some people saying that they've pledged and already have donated, so thank you so much to those who have already given. And if you're moved to become a member, if you want to elect our next tranche of board of directors and just another way to get involved, you can follow along that QR code. And we are very passionate about making membership open and available to everyone. So if there's financial constraints for you, please come talk to us and we want to make that happen. Oop. And before I stop my screen share and pass the mic over to Nathan, do a brief introduction of our topic of the day. Oh, before I do, some housekeeping items. Please keep yourself muted during this presentation. There will be opportunities for Q&A throughout, and you can submit questions directly using the chat function at any time. If for whatever reason we don't get to your question, send us an email. I will put our link. I should also give you our link to our year-end fundraising campaign, which can be found here. And then I'll put the MREA info email in the chat function once we get the presentation going. This session is being recorded and will be available to registrants later this week. So, like I said, the topic we've got for December 2024 is solar readiness and new build design. Engineering and design firms and their clients are often planning for future longevity. While solar PV integration is not always possible at the time of initial construction, there are a number of strategies for building owners to be solar ready. This session outlines actionable insights for architects, engineers, and stakeholders to meet energy needs while preparing for future advancements. And we have Nathan Bronec, like I said, with Cushing Terrell. He's an associate with Cushing Terrell and an electrical engineer. So welcome, Nathan, and you have the floor.
Hey, thank you, McKenna. Let me get my screen sharing here. Get this in a slideshow mode. Yeah, so happy to be here. Happy to talk about solar readiness and new building design. Just a little background on me. So I've been working kind of in the built environment, I would call it, for the last 10 years. Graduated from Bozeman in mechanical engineering, but decided I wanted to be an electrical engineer instead. So it's a little bit of one of those weird things. Technically, yeah, my degree's in mechanical engineering, but I'm a licensed electrical engineer, and I lead our alternative energy engineering group here at Cushing Terrell. And we primarily focus on, on-site solar, battery storage, utility scale solar, anything that's power generation side. So a lot of my work lately has been in California doing remote grid work there, where I'm doing line hardening and fire mitigation strategies and putting in microgrids to uh, reduce wildfire risk. So what is solar ready buildings? I think it's good to look at like what the code kind of says. So the International Energy Conservation Code, which is adopted here in Montana, listed as a section or sections of the roof or building overhang designated and reserved for the future installation of a solar photovoltaic or solar thermal systems. We kind of view that as a little bit broad. I've come up with our own little internal definition at Cushing Terrell where I say a building design that considers and accommodates the installation of a solar photovoltaic system in the following key areas. One, building and site orientation, roofing material selection, structural loading accommodations, consolidation of rooftop equipment, established electrical pathways for solar, and space accommodations for inverters and disconnects. I'll kind of go through each one of these and kind of give an overview of what we look for when we say the building's going to be solar ready. So kind of starting off the top here with the building orientation consideration. Obviously, being in the northern hemisphere, it's ideal that a lot of our solar systems are due south facing. So when we're dealing with gabled or sloped roof buildings, we really want those roof faces to be kind of due south face, trying to avoid any north facing things for obvious reasons. And then on flat roofs, we really want to keep it where our array can still be parallel and perpendicular with the parapets. So we're maximizing that roof area. But knowing that sometimes that can deviate, we've gone through and looked at what the change is, basically for each 15 degrees rotation off of south. And so while there is a penalty there, kind of when you see like, okay, here's a west or east facing array, this was a site that we did in Austin, Texas, where we're seeing an 18% decrease in the generation over the system's annual production. But there are some interesting things that can happen when we start orientating to different directions, especially east and west, where we can start to shift that time of production. And that becomes really important during like a uh, off-grid or potentially a battery storage project, where you can almost start to tailor your load profile and your generation profile and try to get those to overlap a little bit. So, um, like I guess synopsis would be is while it's great to be south-facing, don't get too hung up on that. If there's things on the site that are limiting you from achieving that, um, there's you can still have solar on that site. So the other thing that we kind of really start to consider is the roofing material selection. Obviously, a roof material, especially when we're not putting the PV system on at the start, we really want to make sure that it has a long lifespan. So if you build a new building and say that you can't put the PV on in the first 5 or 10 years, you start to bump up into that lifespan of the PV system and the lifespan of the roofing materials are almost out of sync with each other. So most PV systems, they're going to last over 25 years. And we always want to make sure that the materials that we're using for our roof um, is going to be in that same time frame. So when we look at sloped roofs, gable roofs, um, our preferred material is often like a standing metal seam roof. Um, that's going to be super easy for install later down the road, but and also a long lifespan. However, asphalt shingles are okay if that's the option. Obviously a metal roof is more expensive, so um, most asphalt shingles are workable and stuff. I think the big thing to consider there is just the how long after the asphalt shingles have been laid that the PV system's getting installed. Like I said, if you're in that 10, 15 years down the road, you might really want to start considering like, should I replace this even though it's not due yet, but something could happen and then it's underneath my PV array. And now I have to take the PV array off to fix something. So trying to really factor in those material selections up front, I think is important. For flat roofs, we usually like to see like an EPDM roof or PVC. Those typically have a longer lifespan than like a TPO roof. Um, and most of those, like the EPDMs and PVCs, are like a 30-year lifespan. So kind of jives in well with that useful life of the PV system. Now getting into kind of the structural loading accommodation piece. Now this is probably the biggest impact that a solar ready building is going to have is, we can work with orientation, we can make the roof material work, but um, the major retrofit that would have to come in on some buildings is on the structural piece, and that's a huge disruption to the use of the building potentially, especially if we're having to stiffen up roof trusses and stuff. And so, what we like to plan on our roof structures, if we don't know what the system's going to be and we don't have a final system design, we want to see at least a 2 PSF dead load allowance on gabled and sloped roofs. We feel like this is right in line with what those weights typically come out to be. And then when we start talking like flat roofs, so your big commercial buildings, things like that, we really want to see 5 PSF of dead load over those areas. And the 5 PSF is actually the required amount to be labeled energy or solar ready as far as the IECC goes. So that's where we view the min as 5 PSF. Now, if you have a building and it didn't have a 5 PSF dead load, there are things that can be done to try to accommodate solar on a flat roof. You can look at like a hybrid ballasted system where it has both ballast blocks, so concrete blocks that are holding down the PV system, along with some mechanical attachment points. And we've seen those systems. I've done a couple of them that were hybrid systems, and those come in around the 3 PSF load, um, which is a little bit easier to accommodate if it's an existing building that maybe didn't have, uh, the structural accommodations planned out correctly for it. The other thing I like to always flag especially being in Montana where we can see some really high snow loads in certain regions, is that most panels, PV panels, have a load rating on them of 75 PSF. So if we're looking at flat roof or even a gabled roof layout with those panels, you could start to bump up against the design load condition of the panels and you see some panel failures. Um, I've done a lot of work down in the Sierra Nevadas recently where we're dealing with 300 PSF snow loads and PV. And what we end up doing down there is typically ground mounted systems with very steep angle adjustments during the winter time. Those arrays are often at a 50 to 60-degree angle in the winter to kind of shed the load. But yeah, being in Montana, I think it's important just to understand that snow load piece, especially for flat roofs and gable roofs, just because the roof might not be the best spot for that PV. It might be better suited on the ground. So then when it comes to kind of the consolidation piece of equipment, um, this kind of gets a little bit uh, hard at times. I'm on the electrical side. If I had a preference, I wouldn't see any mechanical equipment anywhere near any of my solar arrays, but that's not always a option, unfortunately. So I think it's important, especially, designers or even building owners, people looking at plans, you should really think about, okay, if we do put a PV system on here, how is the mechanical system set up? And are we trying to avoid having mechanical equipment in the middle of an area that we have slated for PV? Especially because anytime you have a rooftop unit, exhaust fans, anything like that requires a pathway to them if it's in the middle of the PV field. And that just takes up, valuable space that we maybe set aside and had, more robust structural designs done for that roof area. And then we go and put an exhaust fan, and all of a sudden we lose, 6 or 7 panels because we have to have a pathway to that exhaust fan. Um, this was actually the roof layout that we were looking at for a project in Helena at the Montana Heritage Center. Um, Ultimately, the upper portion is what got built out as PV. The lower one wasn't built out for PV. Um, but as you can see on this, all of the mechanical equipment, there's 2 big chillers, several exhaust fans, all of that's kind of co-located on the right-hand side of that building. And that allows to leave a lot of free area on the roofs for us to put PV and not have to worry about, pathways to that equipment. What's the maintenance going to look like for that equipment and all that stuff. So uh, usually you can work around it, but I think it's best as a design side of things that we really sit there and work as a group trying to make sure we limit those obstructions internal to the areas that we've allotted for the PV. The last kind of big piece here is, established pathways in inverter space. Similar to the structural piece, having to go back into a building that's been built and is maybe operational, and have to pull or install conduits. It serves as a big kind of disruption to the building occupants, to the building um, functionality and stuff. If you're expecting electricians to have to be routing pipes or conduits through that building. And so when we do a solar ready building, we're really wanting to make sure we have established pathways up to the roof area that we have slated as that solar expansion point, all the way down to the main electrical room. Now, the number of conduits that you need and the size of them is going to vary. A lot of times when we're talking rooftop solar, we usually are locating inverters up on the roof with that stuff. So we're running a AC feed through the building out to a disconnect right at the service entrance, and then back out of that disconnect into the main switchboard of that building. Um, Typically, I would say for most of the 50 kW systems, 75 kW systems, we're really only expecting a 2-inch conduit running off that roof for that AC feed out to the outside of the building. But I think kind of working with the electrical engineers and the team on how many paths and how many conduits it's going to require. It really comes down to what that system size is. But generally, what we're seeing is 2-inch conduit down from that roof. So the other thing is inverter space. I've dealt with some owners that prefer not to have an inverter located on the roof for maintenance reasons. And so they want that inverter located in the electrical room. And electrical rooms are often pretty tight spaces to begin with in a building. So trying to make sure you carve out a wall space there that inverter can live is really important. And usually what I do on our plans is when we have an inverter that needs to go inside, but that system's either an adult or maybe not getting built right away, is I really make sure to try to show a dashed box there saying like future PV inverter, just so everyone knows like, yeah, there's nothing there right now on that wall, but it's slated for something. So let's try to avoid, putting a telecom board or whatever there. Um, Same thing with outside the building. Most of our utilities here in Montana and every across the Northwest that I've ran into is all require that visible disconnecting means outside the building for the PV system. Um, and with that, you know, you're looking at the building entrance where the meters are and stuff, and sometimes that's really congested area too. So trying to make sure to have that PV disconnect slated out there and a room accommodating it is another important piece that we often run into when we're trying to retrofit existing buildings with solar. So now trying to just get into what we like to show on a drawing. So this was a building that we did that was wanting to um, have a future PV area kind of designated on it. Pretty simple flat roof building. Um, Typically, when I'm doing these, I do like to do a quick layout of what those panels are going to look like on the roof, just so I can tell the owner, like, hey, this space that we've set aside with today's panels is going to accommodate, 75 kW or whatever. I really think that's important so the owners know what they could potentially fit on that roof area. And then that also just helps the design team, the mechanical engineers understand like I have this dash box on the roof that says future PV, but I don't know what that actually looks like. Are they actually going to use that whole area? Like what's going on? So that's the one thing that we really like to do. And then we always call out what that structural dead load should be. So since this was a flat roof building, we were making sure to call out a 5 PSF of dead load allowance in that dashed area. And then we also called for two 2-inch conduits to be ran down from the PV system through the roof space and then into the electrical room. And we showed a rough diagrammatic pathway there on the left-hand side. And that's what those dashed lines are, is the, estimated runway. So the electrical contractors and folks understand where we're trying to route those, and then they can also get a rough takeoff on them. And so usually when we're doing the PV ready buildings, this is all we show on our plans. I think it's important though that it does get shown on plans because um, who knows what happens with that building in 4 or 5 years. The design team that put that building together might not be around at that point. And so it kind of conveys to the owners, hey, this is the area that was slated for that PV system. It was supposed to have 5 PSF of dead load allowance in it, and it just really simplifies the process when that system needs to get installed later. Then kind of another consideration that I just wanted to throw in here, and I think McKenna and I were talking about maybe even doing a follow-up thing here, but bouncing back to that Montana heritage system. So a lot of times we kind of run into, obviously, with like Northwestern Energy, net metering is 50 kW. You get in with some of the co-ops, it might be 14 kW, 12 kW, like some of the co-ops here in Missoula. But I think it's important to note that like your on-site generation, it doesn't have to be capped at what those net meter agreements are, and that's what we did on the Heritage Center is rather than doing a net metered system, we did a behind the meter generation, non-export. So basically we consume all the power on site. We size that system so it rarely ever exceeds the base demand of that building. And so um, for that, it's actually a pretty simple process, So we ended up on the Heritage Center, we're at 120 kW of solar generation on it. And when we at first started that, we were only at like 50 kW, and it was 2% of the electrical usage. And now we are able to get some more lead points and stuff like that by going with a bigger system and trying to maximize the on-site generation for what that load actually is. And so what that looks like is a level 3 interconnect with NWE, if that's the utility that you're on. And it's a $200 fee. The application is fairly simple. The big caveat there, though, is uh, what you end up having to typically do is have a protective relay then on your PV system that has reverse power protection built into it. So if we are over generating, it shuts the PV off, so we can't push power back to the grid. Um, doesn't shut off the power to the building, but it just shuts the PV off. And then with that, we also have to usually install smart controllers for those inverters because we're going to throttle them up and down to try to follow the building's demand versus always just being at the full output and pushing power back onto the grid. So I think that's kind of an important one too when we go back to, okay, a solar ready building, especially if it's a bigger commercial building, for example, a 50 kW system might only take up a fraction of that roof area. So yeah, we could say, okay, this is the roof area that we're going to allow for the solar system because that's what net meter says, or that's what like the net metering agreements currently are is 50 kW. Or you could be like, you know what? I know my building load's going to be a lot higher than 50 kW. We're going to use a lot more power than we would ever generate off of a 50 kW system. So why don't we just go and size for what the usable area of that roof is? Because we could do, a behind the meter generation interconnect and generate more power and offset more on-site usage. So that's been a big one that we've really started to push here, especially for our commercial clients and stuff, is, you know, actually building solar systems that are a meaningful benefit to their system. Not saying that 50 kW system isn't meaningful, but when you're dealing with a 2 or 300 kW load on a building, 50 kW is not really moving the needle that much. And so we like to really start to model these systems and figure out what's the best or the biggest system we can do that we're not exporting power. And then maybe we even consider looking at battery storage on site and storing that excess power rather than throttling the inverters back. So anyways, that's kind of I think the high level run through of what we look for when we're doing like solar ready building designs. I guess I'll kind of open it up here for questions and anything else.
Great. Thanks, Nathan. Really, really, really good content here for us to chew on. There have been a few questions in the chat that I'll start with first, and as we go on, um, if those who have questions want to write it down in the chat or raise your hand and unmute yourself for a good discussion, we're happy to do that. I think we've got a good sized group for that kind of environment as well. So starting out, this was on maybe the second or third slide having to do with roofing materials. TPO stands for thermoplastic polyolefin. I think, well, that's how I would pronounce it. Maybe someone else would pronounce it different, but could get into a bigger question here, Nathan, about if you, in your experience, or also in your company's experience, have seen an evolution of roofing materials that are better suited for increasing lifespan. Are we seeing a change there, or does it seem fairly stagnant? Yeah, what are you seeing in the industry?
This would be a question that I think I would love to have our envelope folks answer, and we could follow back up with it, McKenna, because I know enough to be dangerous when it comes to roofing materials. I'm an electrical engineer by trade, so I don't pretend to really understand everything. But Pat Todd with our group here, he deals a lot with the envelope and especially roofing materials and stuff. And I'll bounce that one off of him and see what his thoughts are on you know, newer materials coming out with longer lifespans and stuff. I think that would be a good one. So
Great. Another question here coming from Mark Judeman. We know that if the client is asking for solar readiness, that's one thing as far as Cushing Terrell's approach to integrating that into designs. But Mark is bringing up a comment of seeing a lot of new buildings that don't seem to look very solar ready without being able to look at the plans ourselves. So, is it uh, is it common for engineering, construction, and design firms to be discussing solar readiness in the general client interactions, or is it always driven by the client suggestion that you take it and run?
I think it's a little bit of both, a little bit of A, a little bit of B. So yes, often very much a client-driven thing, especially when we say, hey, we're going to be solar ready, but that's going to add some potential cost to your structural envelope or your envelope costs or things like that. So there is a impact there with the owners as far as the construction costs. And so um, we do try not to force it on the owners per se, because at the end of the day, it's their money. But a lot of times when I'm having these conversations with our architects and stuff, and they're like, hey, the owner kind of is thinking this, I always try to frame it of like, you know, here's the added cost of doing this structural now. It's actually pretty minimal in the grand scheme of a whole commercial project. We're talking fractional percentages here of added cost to do this. And then I think it's important to then, when we have those conversations, I always try to preference it with the owners is like, we can always have the, renewable energy piece and talk about, carbon reductions, things like that. Obviously, for certain building owners, they don't really care about stuff like that. They aren't really worried about the sustainability side of things, unfortunately. But I also think there's always a way that we could preface this on-site generation of being like, this is an asset that we're going to put on your building, and it's one of the only things that we can put on your building that's actually going to generate revenue for you over the lifetime. Like I can show, based on construction costs and things like that, that most PV systems currently are having a 14-year payback, 12-year payback in Montana. That means that for 11 to 15 years that thing is offsetting your utility costs and making you money. How do you can't really claim that with a rooftop unit, right? Or any other thing that you're going to include on your building. And so I always really enjoy having those conversations with uh, building owners and stuff and saying like, we can do these things now. It's going to add a little bit of the construction costs, but what it does is it sets your building up to be able to do this in the future, whether or not you're interested in it now, but you should be interested in it because it could pay back on itself way before the lifetime of the system. And so there's just those, I think, a lot of misconceptions out there with PV and the paybacks and stuff on that. And usually when we have that, the owner's like, yeah, let's do that now. And then I'll consider whether or not I want that capital expenditure in the future. So it really, I think it's important as designers that we do try to have those conversations. Cushing Terrell, we are signed on as a AIA 2030 pledge, which means that we're trying to reduce the greenhouse gas emissions of all the buildings that we design. And so we need to have those conversations with the building owners, whether or not they're really wanting to. But at the end of the day, yeah, it's up to them on whether or not they're going to approve us to make those accommodations on the plans and the structure. So
Right, right. And because I know Cushing Terrell and you on a professional and individual level have worked on projects beyond AHJs and jurisdictions in Montana or outside of Montana's borders, have you seen greater adoption of solar ready design where David Saslov here mentions conditional use permitting processes that integrate a requirement for solar readiness? And I would think yes, if there's a requirement, then yes, it's likely being talked about
yeah,
more often because it's required. But how have you seen that evolve, either with or without those explicit
yeah,
requirements in building codes or appendices?
yeah, and so like I said, the IECC already has a, section about solar readiness in there. It's not a enforced section in Montana in a lot of states, but we are running into it, Washington with their energy code. They require their buildings to be solar ready. Same thing with Denver. I'm not super familiar with the exact code calls out on there, but I'm pretty sure it says like 40% of the usable roof area has to be accommodating for solar. Um, and so it's not so much conditional use permits and stuff like that that are being placed. It's just a part of the building code there. It's when we do buildings, you have to follow the energy conservation code, you have to follow the building code. It's just in the code. It's a code requirement that the HJs are looking at the plans and they say, yep, it has to be on there. So there's definitely a lot of markets that are not really letting owners have a say in that anymore. And they say, you know what, for the fractional construction cost add here, we should just do this because the amount of times that I've gone to a building and the owner has said, hey, we just bought this building. We'd really like to put solar on it. And you go through and you're like, okay, well, you have to go reevaluate the structural roof calcs. And is a building made in the 70s or 80s, and snow loads have changed dramatically since then, and requirements have changed, and all of a sudden you're saying, this building could have had it, but we got to do like 30, $40,000 worth of structural upgrades to do that, and it just wrecks the economics of the system. So I think it's value add to just do this stuff up front for sure.
So if I could just follow that up. So the answer really to my question is no, you're not seeing conditional use permitting as a vehicle for this communication yet in many places.
Correct. I think it's not really tied with conditional use permits. It's tied with actual just building permits in general.
Okay, thank you.
Yeah. Yep.
Thank you. Susan asked during the presentation, and I think you actually answered as you were speaking, but we could speak more to the protective relaying required with level 3 interconnections and how battery storage integration for some buildings has evolved in the, recent years that you've observed or that the sector has observed, and how that could interplay, what cost considerations are, and how that adoption has looked.
Yeah. So as far as protective relaying, what we usually do, what we did like on the Heritage Center and stuff is we use a Schweitzer relay. It's a really common relay for utility applications. And so we use an SCL 751 relay, and that has its own basically PTs and CTs that are seeing their monitor building. And so when you set up those level 3 interconnect, we're required to either have a min import or a min export amount. Like there's a slight buffer there that NWE requires. For example, like on the Heritage Center, we will always be pulling in at least 12 kW of power. And that's what the relay is looking for, is that import power coming in is at least 12 kW. If we hit that threshold of 12 kW or less, it sends a shut trip signal to the breaker and opens up that breaker. And so as far as added cost on a project, SCL relays are $3,500 and you're talking, maybe having to pay a relay engineer $1,000 for the programming of it. It's really not a huge cost add on these systems. As far as battery storage goes, um, haven't seen a huge adoption of battery storage yet in Montana on too many commercial projects. And I think a big piece of that is just how a lot of our tariff rates are set up and things do not really incentivize batteries per se. Uh, but I've done a lot of battery storage projects in regions that have like time of use rates and things like that. And what we see is, we'll typically overbuild solar. We'll be generating more power throughout the day than what the building needs. We aren't exporting that power though. We're storing it in the batteries and then discharging those batteries at a set determined time, basically with the battery management system. And so oftentimes if it's a um, residential building, for example, our peak loads are going to be at 5, 6 o'clock at night when people are getting home and starting to cook dinner. Commercial buildings typically are actually kind of peaking throughout the day. But anyways, that's like the battery aspect, I would say, hasn't really kicked off too much in Montana. We've done some bigger projects. Um, and by that, I mean like multi-megawatt battery projects, but they're not really the owners of those are kind of looking at them as grid assets versus, building assets per se. And what I mean by that is they're entering into marketplace and they're waiting for, ISO controllers, grid managers to send dispatch signals and say, hey, our grid is peaking right now and we need more generation to come online. And so they send a dispatch signal to the batteries to do that. Um, we've done a couple projects like that in Idaho right now that is going off of that. And we're looking at a couple things for some clients here in Montana that will have capabilities like that. And that's a whole different scheme basically. Yeah, it's kind of tied with a big commercial building, but they're dispatching that battery based on what the grid needs, not what the building needs. So it's kind of a whole different market value there.
Right. Different question. Question from George Bailey here about how you might see applications of hydrogen interact with batteries or coalesce with battery deployment. And George, if you're on, maybe you could speak more to what you mean about hydrogen and batteries, because hydrogen can be a battery or can be a storage mechanism in itself. But
Yeah,
George, you
I'll jump
on?
in real quick.
Hi.
We have a project at the airport. Nathan knows way too much about it, but um, we're looking at if you think that large users like airports and hospitals, they put in diesel generation for backup power, and in talking to anybody that maintains that system over the 30-year life cycle of a diesel generator, the use case is probably less than 1%. So the idea would be to make during your high period in like summer, overbuild your solar, make hydrogen, and then instead of having a diesel generation system for your backup, it would be a hydrogen and it can do that level 3. So in other words, they can decarbonize their power, not just when there's an emergency, but during the every day of operation. So I was just asking, are you seeing anybody other than us, Nathan, looking at that solution?
Yeah, I mean, most of the hydrogen generation stuff, George, that we've kind of looked at lately has been longer term storage. So like um, it's been like a battery's great when you're wanting to charge and discharge within a 24-hour period, right? Like that's what they're phenomenal for. But when we start talking long duration storage, aka northern latitude areas that have really high generation capabilities for solar during the summer months, where that wanes off in the winter months, um, we've seen a couple of folks that have asked, and we've kind of did a high level look at basically over generating during those high generation months of the summertime and storing that as hydrogen and then using fuel cells to basically, supplement power in December timeframe, right? So trying to level out that production over the life of the system, and that's where hydrogen, I think, one of the applications. The other one, George, is obviously in the backup generation system where you might run your generator for 10 minutes a month for exercise, and you might see an outage once every 3 years that runs for an hour. Um, yeah, having hydrogen for that makes a lot of sense too. But we've seen it as kind of a capability of conserving energy or storing energy for 4 or 6 months out kind of thing, um, which has been an interesting piece for sure.
Next question on the list here comes from Slim Miller asking about how rate structures change for non-net metered level 3 interconnects. I know this is specific to the interconnection agreements with Northwestern as our largest utility in Montana, but Nathan, can you speak to any rate structure, i.e. demand charges or other considerations that a level 3 interconnection would demand of a client to evaluate?
Yeah, so right now, for example, like that level 3 interconnect we did with the Heritage Center, it still uses their general service rate um, tariff so that it's not changing the price per kilowatt hour or the demand charge that a commercial building would see in Montana. Um, some utilities on the East Coast that we've worked with and stuff, or and then in the Pacific Northwest, depending on the generation size, um, if you're in the multiple megawatts, say, of behind the meter generation, we've seen utilities and worked with utilities that had basically um, uh, backup or standby charge rates for that power, meaning that, yeah, this, it's very common in like gas generation plants and stuff like that if it's behind the meter. But um, say you have like a 1 megawatt generator plant, right, that's running megawatt at any time of the day, right? And then it goes offline. Well, all of a sudden the utility's having to make up for that 1 megawatt of generation. And so they have basically a way of collecting standby charges so they're able to potentially have to if they have to spin up a you know peaker plant somewhere or something to accommodate that sudden shift of power, that comes online. And when we do studies for especially level 3 studies where we're having to talking about overbuilding and stuff, those are all things that we really try to factor in. But right now in Montana, especially with the solar systems we're talking about, a level 3 isn't really triggering any new different tariff than what you currently are paying for. So
A couple more questions here as we get to the top of the hour, and we will wrap up by 1 o'clock, if not a little earlier. Susan Belo asks, where does Cushing Terrell make this presentation? At trainings or conferences? How often is this content being shared within your networks?
usually I share it a lot internally. I haven't, this is the first time I've ever presented outside of the walls of Cushing Terrell about it. So, but yeah, definitely it's a thing that our sustainability group here and I definitely tried to share with everyone. So.
Well, if you're offering, we will take you up on it to have presentations like this in various spaces where it could be useful. Then another question, suggested ways to shorten the payback period of that, 11, 12 to 14 years. I mean, an obvious one is finding other ways to cut costs, but do you have other insights on that, Nathan, based on your experience?
Yeah, um, obviously, like the big benefit right now is the tax, the investment tax credit, right? I think the other thing on the payback that we see as a big shortening of that is when I say 12 to 14 years, I'm really talking about like those, smaller systems. Um, Theoretically, as we get larger PV systems on a single location, the construction cost per watt should drive down. Obviously, our generation costs then go down, so we're generating more power for less money per kWh, um, which then impacts the payback. So I've seen some larger systems, especially like when we start talking megawatt size systems, and that's the hard part, is not super applicable to a building usually, unless it's like a big campus, right? Um, but those can get down under 10 years for sure. I think the other thing is just to potentially like being able to couple with batteries and add those batteries as a dispatch benefit to the grid. That's where we've seen a lot of batteries actually show a really good payback, is when we stop using them just for like load shifting, but actually entering into some of those markets. And I don't have the name off the top of my head, but there's been a couple companies that we've worked with that manage that for commercial customers, basically, where if they had a 250 kW battery, that's like a 4-hour battery, right? That person or that company can help negotiate and enter in those contracts with those RTOs, the grid managers, things like that, um, to dispatch that battery. And when you're doing that, a lot of times utilities are paying $200-300 a kilowatt hour because it's such a short duration that peaker plant's coming online. And so when you start talking about having 2 of those calls a year, it really makes the economics of the batteries shift quite a bit. So, but yeah, scale is obviously the biggest thing that I think impacts pricing on the solar side of things. So.
Right. Then final few questions here. Hopes for the best case outcomes for the 2025 legislature. I know that Cushing doesn't get as involved in the policy side of things. You're dealing at the regulatory level with tariffs and building codes, but can certainly say for MREA that our best case is improving access to that scalable output that Nathan was just referencing. So we're supportive of community solar as a policy concept that will be at the 2025 legislature. So that's one. And then another question that we just didn't spend a ton of time on early on in your slides. It says, this comes from Paul Cheetah, how does roof slope pitch affect solar output? And you had a nice graph. Maybe we could spend just a little more time explaining those reference points. Yes.
Yeah, I actually had I should have, let me stop sharing. I got a different graph that actually talks about this. That's actually a little bit better. Let me find that real fast and I'll pull it up because uh, we did a little study on this. I used to be a big proponent of um, mechanically attached systems because they were at a steeper angle. And I've kind of switched my my thought process on this with ballasted systems now, because you can fit more panels on the roof and make up for that lost production. Let me see. So this is, share my screen here. This was a slide I kind of put together for our company internally here. And so we kind of looked at latitude. So, 20, 30, 35, 40, 45, Montana, we're kind of in this bracket here. And then what the energy yield is per kilowatt hour per kW. So granted, this kilowatt hour per kW yield kind of varies based on climate and stuff like that. But as you can see, it's 5-degree, 10-degree tilt, we're at the 1500. And then ideal tilt for us would be like a 35-degree tilt system, and you're kind of more in the 1700. I can't remember what our site was for the 40-degree or latitude location. So, but anyways, obviously there's a slight trade-off there in roof slope or racking pitch compared to the generation. But what I have found, so say that if that 10-degree tilt versus the 35, you're taking an 8% decrease in that. But to space out 35-degree panels on a roof with a mechanically attached system, you can easily fit that extra 8% that you lost in production with just more panels on the roof. And I found that trade-off there is actually a cheaper aspect because mechanically attached systems are, um, a lot of roof penetrations that end up happening, and they're prone to leaking and other things like that. So, yeah, I don't get too fixated on system tilt anymore when it's on a roof, because I just go with the ballasted system and I try to build out more. So,
And you did mention that the new Heritage Center Museum opened 2025, I believe, summer 2025. They are using a ballasted
yep.
system, which was a design that you worked on. So pretty cool to have that full circle. And for anyone going to be in Helena next year, go check out the museum and the solar system on the roof if you can see it.
Yeah, and that was actually one that I started out as a mechanically attached system, and then we went to ballasted, and I kind of was like, huh, that didn't actually impact our total production, and it's actually a higher. The roof area that I had is the same, and I'm producing more power now than I was with the mechanically attached system. So.
Nathan, I'm sorry, how do I interpret a summer energy target in December in that bar graph? Why are there 3 bars for each month when some are clearly not in the season that
So
they're advertised?
yeah, so that was a that upper graph was was for plotting where our peak energy usage was on a project. And so it was just trying to figure out like, okay, we want to target peak energy during the summer or annual peak or winter energy. And so so in Bozeman, for example, if we were targeting a summer energy target, meaning our peak output is in the summer months, that's, assuming that we're probably like a 15 to 20-degree tilt on that system. Whereas the winter energy target is, trying to provide the most power in the winter months. And that's a, 40-degree tilt in Bozeman. And then the peak annual average energy was like the in-between piece there. So
I see. So it's either a flatter or a steeper bell curve.
exactly. And it's just kind of like saying like, how do we want to tailor that generation? Do we want more power generation in the winter months, but then take a penalty during the summer months? So that's what that green line, that green graph, you kind of see where it doesn't really peak up in the summer months. It's kind of flat through there. Or do we want, high energy output in the summer or kind of a in between there? So
Makes
that was
perfect sense.
that was for a remote grid
Thank you.
project. So, yep.
Awesome. So we're looking at the top of the hour, so we'll wrap it up here. Thank you, everyone, who attended the Exploring Energy series this year. We're excited to see you again in 2025. While the legislature is in session, we take a pause on these monthly Exploring Energies, so we will be back at it in May. So we'll take a little winter break. Please stay in touch with us. We hope you have a restful holiday season. I put our Power 2025 campaign in here one more time, and we'll call it a day there. Thanks everyone for joining, and we'll see you next time.